Well, welcome back. This is Tom McGibbon. I'm Director of the Cybersecurity and Information Systems Information Analysis Center, or CSIAC. Last week on December 5th, we had a presentation by Taz Daughtrey on the title here being Software Security Growth Modeling. Thought I would ask him a few follow-up questions. And so first of all, I'd like to welcome you, Taz.
Thank you, Tom.
You bet. You bet. The first question I have is, what are the assumptions and limitations in the use of reliability growth modeling? Plus, what are some of the additional considerations for security if you're going to do security growth modeling?
Yes, there are a number of mathematical models that are behind any attempt to do reliability growth modeling. Once again, the idea is that you're making some sampling. It's actually sampling with replacement. You repair and replace every time you run a test. When you discover a defect, you fix it, put it back in service. And as the rate at which you're encountering, and supposedly the lower rate at which you're encountering defects as you go along will give you some indication of how reliable the system will be in operation. The mathematical models often, as most mathematical models have to be, are simplifications. One of the simplifications is that repair process is perfect. There are actually only, as far as I know, a couple of dozen models that really take into consideration the idea that when you find a defect, that is, when a test fails, you might not perfectly fix that problem, or more likely, you will also possibly create a new defect when you go to fix the original one. So we have to be careful about those kinds of assumptions. Also, there is underlying many of the mathematical models the assumption that the defects are fairly randomly distributed. And the thing that we know from a lot of empirical data is that it's a Pareto-type principle with a vengeance. So 80% or more of your defects come from 20% or fewer of your sources, say modules or methods in your software. So those are the sorts of things that already have a limitation. And then one of the ideas of applying a reliability growth model to security issues is based on the idea that there's a subset of the defects that would affect reliability are things that could be exploited for security as a security breach. And so that subset of defects are known as vulnerabilities. So there's the additional issue of understanding how likely you are and what the distribution is of encountering the defects that are actually security vulnerabilities. As well as the whole idea of whether what you're doing in your testing, as basically the way in which you're trying to use the system or even to abuse the system, adequately models the way someone would attack it. So one of the things that's underlying most of the reliability testing is that you are profiling the way usage would actually be distributed, and therefore, you have to make a lot of assumptions if you're thinking about testing for security purposes, because you basically have to imagine the various modes and the distribution of modes in which people would try to attack the system. So I think that it's a much more difficult problem, but it's probably worthy of attention because it's one hope that we have of trying to decide when the software is good enough. We have that in terms of making a release decision for the broader issue of reliability. For the more specific issue of security, we really would like to know when the software is good enough, and this, at least I believe, offers some promise to move in that direction.
Okay, very good. So how much time and how much effort or cost is required to implement this model in a small to medium enterprise?
Well, the model itself, let's say the reliability modeling, is really simply a data analysis. There are a number of tools like the SMERFS, S-M-E-R-F-S, tool, which is actually a free public domain that incorporates, I think for that particular tool, 17 different reliability models. And so it's really only taking the data that you're already going to be accumulating as you're running tests and entering it into a front end, such as the SMERFS tool, and depending on whether it's the time intervals between tests that fail or another type of distribution, you're basically just running an analysis against those underlying models. Now, there really are not any security models yet, and so basically what I'm sort of trying to lay out is the possibility of there being some analogous type of analysis to be done. But essentially you're gathering that data anyway because you're running the test. The test is the sampling process, and then based on the frequency with which the test revealed defects, and specifically for security issues, the frequency with which those defects are exploitable, so they're vulnerabilities, gives you some insight into how much you can count on the software, and then as you improve the software by fixing those defects, removing those vulnerabilities, there ought to be some distribution that begins to give you some idea of how much better you are and whether you're good enough. So for reliability, it's pretty straightforward. The tools are available freely, and it's a matter of just plugging in data that you're going to be accumulating anyway. From the point of view of doing this as a security analysis, it's still a work in progress.
Okay. Very good. Now, for complex systems or systems of systems, how many different profiles should we expect to define? Dozens? Hundreds?
Well, this goes back to the type of statistical acceptance testing for reliability targets that was championed by John Musa. And of course, the idea here is that the testing really needs to replicate the distribution of inputs that you're going to encounter in the actual operational environment. The simple-minded example that I use is you go to a self-service gas pump. There are 3 grades of gas. But if you were going to test the software that was driving that particular application, you wouldn't distribute uniformly, randomly across those different buttons, because if you ever look at those buttons, you know the cheapest gasoline button is the one that's well worn, and almost no one picks the most expensive. So if you actually wanted to get a profile of how that was going to be encountered in operation, you'd want to run the test in the same proportion, the same distribution. So say 85% of the time people push the button for the cheapest gas, 85% of your test should also be for that function. Now that's a very simple component. That's a simple system and one component, one input value. So certainly the issue would be as you get to very complex systems and systems of systems, the distributions, the profiles, just in terms of the permutations, the number of inputs and all the interdependencies grows pretty dramatically. And so it's just a level of, it's really, if you want to think about it, it's a level of granularity that you think is representative. Think about a weather map. The weather map at a large scale and modeling of weather at a large scale, the kind that you see on the evening news on your local TV station, is the cells are pretty large. That is, here's what's happening in this state, here's what's happening in this state. To do a more detailed analysis, you have to drill down. And so I would suggest that even in a complex system and system of systems, there's a high level in which the granularity isn't that great, that you get some insight. And then, as I just mentioned in the previous question, because there's a distribution, there's a clustering effect, probably that high level of distribution would give you some idea of where you could then focus your effort, and you could drill down, and then you could have the granularity smaller in a smaller subset of all the tests. So just from that point of view, I would think you'd probably sort of peel the layers back step by step in that way.
Gotcha. Okay. Finally, how would you apply risk-based security appraisals throughout the development lifecycle?
Well, risk-based basically is saying that, again, you don't uniformly distribute your attention, you don't uniformly distribute your effort. You need to think about the risk exposure. And in the case, the classic definition of risk exposure is it's the product of the probability of the occurrence and the consequence. And so one of the things that people would often not be thinking about carefully enough is they're simply going to look at what's the most catastrophic thing that can happen. But if the probability multiplies that out to a very, very small risk exposure, then worst case scenarios might not be worthy of your attention as much as something that has a lower consequence, a lesser consequence, less damaging, but has a higher probability so that the product of the probability and the consequence is greatest. So I think that the first thing that you would want to do to be risk-based is to begin to do that kind of analysis. then focus your attention. And obviously, throughout the life cycle, you begin at the real leverage point. The real fulcrum there is working through your requirements. There's more risk to the extent that the requirements are ambiguous or unclear. The requirements are readily changing, and the so-called scope creep as a project goes along, as we're adding new features. Those are things that early on in a life cycle that we need to be aware of and we need to be monitoring. And I would suggest that in addition to your probability and your consequence, there's also another factor of uncertainty. And so you have greater risk to the extent there's uncertainty. And so as you converge later on, you'll know more and more exactly some of the probabilities or some of the consequences. And you'll have to keep reevaluating. So that's the reason it's an ongoing process as you move into design, implementation, integration, testing sequences. You'll need to keep reevaluating that. But always keep in mind that what you really want to look at is the return on your investment based on where you can reduce your risk exposure. So you either try to avoid the risk, that is, reduce the probability of the thing happening, or you try to mitigate it, which is decreasing the consequence. And to the extent that that product can be reduced, you could even do a type of cost-benefit or return on investment. And so I would suggest at any stage of the development process, to the extent that you first of all can understand what your risk exposure is, even in sort of semi-quantitative, quantitative terms, and then see for various types of activities, appraisal activities or design alternatives, which one gives you the greatest reduction in your risk exposure. That's where you ought to put your emphasis.
Okay, well, thank you very much, Taz, for all your information, this presentation that you gave last week, as well as answering these questions. And so hopefully we can get you back soon to give another presentation. So thank you again.
My pleasure. Look forward to it, Tom.